Termodinamik dersi bir ana ders olarak okutulmalı. Sadece şey değil, mühendislere değil. Eğer meraklı olanlarınız varsa internete girip ister İngilizce ister Türkçe sosyal antropi, ekonomik antropi konularının çok geniş olarak dünyada incelendiğini, işlendiğini de görürsünüz. Dolayısıyla alanı genişletmemiz gerekiyor galiba. Buna diyetisyenler de katılmalı bence. Termodinamiğin birinci kanunu her diyetisyen çok iyi öğrenmeli. Almadan vermek, vermeden almak mümkün değil. Dolayısıyla ne kadar giriyorsa o kadar depolanıyor veya jimnastikte vesaireyle bunu atacağız demektir. Bunu öğrenmeleri gerekiyor. Politikacıların çok iyi termodinamik öğrenmeleri gerekiyor. Yorum yapmadan söyleyeceğim. Biz zaten toplum olarak termodinamiği biliyoruz. Diyoruz ki almadan vermek Allah'a mahsustur. Vermeden almak da hırsızlıktır. Aslında bunu çok iyi biliyoruz. Teşekkür ederim.
Hakkı Bey buyurun. Kendinizi sizi herkes tanıyor ama bir de tanıştırıverin.
Abdullah Bilgin, hemen çok kısa bir şey söyleyeceğim, zaman almayacağım. 2 hafta önce Yunus Hocam'la paylaştım, Birol Hocam'la da. Siz bir yıllar önce okuduğumuz termodinamikten bugün güncel örnekler verdiniz. Bir tanesini de ben ilave etmek isterim. Bundan sonraki sunumlarınızda belki kullanırsınız. 2-3 hafta önce ortama verdiği ısının yarısını kazandan, yarısını kendinden karşılayan bir radyatörümüz de piyasaya sunuldu. Hayırlı olsun tabii. Maalesef bunlar bu ülkede tutuyor. Üzülerek söyleyeyim. Hocam bunu da burada paylaşmış olayım. Teşekkür ederim.
Evet. Başka konuşmak. Buyurun.
Ben bir anekdotla devam etmek istiyorum. Yıl 1995, Alarko zaman yönetimi eğitimini verdiriyor. Belki siz oradaydınız. Hayır, başka, hocamız başka. Hocamız bayağı profesyonel bir hoca ve Sayın rahmetli Üzeyir Garih de, ben de dekanım. Arzu ederseniz siz de eğitimimize gelebilirsiniz dedi. Ve de çok büyük bir fırsat olarak gördüm. Çünkü yetişemiyorum birçok şeye. Koşuyorum. 24 saatimi de versem yetişemiyorum. Ve 95 ilk yılım dekanlıkta. Koşa koşa gittim Alarko binasında. Hocamız başladı anlatmaya. Ara verildi. Ve gittim yanına. Dedim ki siz termodinamiğin 2. yasasını anlatıyorsunuz. Şaşırdı. Benim eşim makine mühendisi dedi. İkinci günde gelecek. 2 günlük bir eğitim. Akşam bir tartışayım. Yarın geleyim dedi. Gerçekten de eşiyle herhalde epey bir konuştu. Geldi sabahleyin, haklısınız dedi. Şimdi zaman yönetimi gerçekten termodinamiğin 2. yasası. Hocam, müsaade ederseniz zamanımızı iyi kullanalım ve de programımıza uyalım. Çok teşekkür ediyorum.
Şimdi bir dakika. Hayır. Yok, bir şey söyleyeceğim. Bir dakika. Bir dakika. Vereceğim, alacağım. Şimdi evet. Şimdi genellikle böyle termodinamik mühendis olmayanlar diyor ki bu hep diyor entropi diyorsun. Entropi nedir diyor. Mesela, şimdi dedim ki kardeşim entropi düzensizlik demektir. Bak sana bir misal vereyim dedim. Bizim sitede genel müdürler var dedim. Ben sabahları gidiyorum, arabalar duruyor. Sonra bir işim oluyor, geri geliyorum, saat 9:30 oluyor. Genel müdürlerin arabası gene orada dedim. Şimdi genel müdür 10'da gidiyor, oturuyor masasına. Diyor, şimdi otur muhakkak bir çay gelir dedim. Arkasından dedim şeyler gelir, gazeteler gelir dedim. Öğleye doğru arkadaşlar telefonla. Bunların hepsi dedim entropi production dedim. bu genel müdürün verimi düşüyor. İşte entropi böyle bir şey. Kardeşim entropi düzensizlik demektir. Bu kadar basit dedim. Hoca mesela biz derse geliriz. Tebeşir yok. Nerede ders anlatacağım böyle. Notların karma karışık. Kitabın karma karışık. Düzene sokana kadar dersin yarısı geçer. İşte entropi ürettin. Verim de sıfıra indi. Evet. İşte böyle.
Hocam vereyim bunu müsaade ederseniz. Lütfen. Çok rica. Çok sevgili hocam. Burada her hocam çok değerli ama Sadık hocamın yeri ayrı.
Ha, teşekkür ederim.
Gerçekten çok teşekkür ediyoruz. Şöyle vereyim hocam. Evet.
Çok teşekkür ederiz.
Sizden de sertifika vermenizi rica etsek.
Evet tabii. Hep beraber
var.
çekelim mi?
Neyse sonra alırız.
Yok hanım kızım getirecek de. Bir dakika gelecek.
Teşekkür ediyorum. Evet. Birol hocam. Teşekkür ediyorum. Sağ olun.
Evet. Birol Bey.
Her şey geliyor arkadaşlar.
Birol Bey. Buyurun.
Biraz beklemek
Her şey,
bilmemiz
her türlü düzenli.
Çok teşekkürler.
Cemil'ciğim çok teşekkür ederiz. Gayet güzeldi, çok güzel.
Sağ olun. Çok teşekkürler. Tebrik ederim.
Çok teşekkürler arkadaşlar, sağ olun.
Dear guests, this is the end of our panel section. We all thank you all speakers of the panel and the moderator, Professor Dr. Sadık Kakaç, Emeritus University of Miami and TOBB University of Economics and Technology. We have a short coffee break for 10 minutes now, and we will come back here in 10 minutes for the invited speakers session. Thank you very much.
Good afternoon, everyone. It's my pleasure to introduce the next speaker of the tech session number 4. The session title is I need to, so that for me to read. The current status and the future potential of additive manufacturing in HVAC and energy conversion system. The speaker we have today is Dr. Michael Ohadi. Mike is a professor of mechanical engineering, co-founder of the Center of Environmental Energies Engineering, and a director of Smart and Small Thermal System Laboratory at the University of Maryland. He received his PhD in mechanical engineering from the University of Minnesota in 1986 and served as assistant and associate professors at the Michigan Technological University. And he joined University of Maryland in 1990. Mike is a member and a past chairman of ASME, Process Industry Division, Executive Committee, and also a past chairman of ASHRAE TC 8.4 Committee, which is the refrigerant to air heat exchangers. And also a member of ASHRAE TC 9.9, which is for mission critical facility. And let's give a very warm welcome to our speaker.
Thank you, man, for your introduction. Happy to be here again. Thank you again to the organizers of the conference. Takes a lot of time and effort, Dr. Nilüfer, the rest of organizers. And the topic is additive manufacturing. I'm not sure how many of you have heard about additive manufacturing. Anybody in this room has heard about additive manufacturing? Dr. Nilüfer, anybody else? Wow. So I'll go very slow, and hopefully by the end of this lecture, you would know what additive manufacturing is, but I'm one of the big supporters of innovation. So I like the previous lecture that focused on innovation. I think from here on, we really need job creators. I heard on the background, my Turkish is not that good to understand all of it, but I heard on the background that we were discussing thermodynamics and how important it is. I would say thermodynamics is important, fundamentals are very important, but we have to ask our students and young generation do something with thermodynamics. Just learning thermodynamics on its own, unfortunately, is not going to help. But if you do thoroughly understand the fundamentals, as technologies change, then you can make use of them. Additive manufacturing is a tool, is a technology, is not fundamental, as you will see today. So I will give a brief introduction on the technique, and then would look at case studies. I have gone through benefiting from additive manufacturing myself. So hopefully by the end of today, you will become a fan of additive manufacturing because it's a great tool in terms of next generation devices. I already told you where I'm from, so please, if you visit the Washington area, we'll be happy to show you our additive manufacturing labs. I'm not sure if Dr. Nilüfer has seen, but recently we acquired some machines, and the students are really creative in what they could make with these machines. Guiding principles, additive manufacturing for energy HVAC applications. I have some slides that I took them out for the purpose of time, but there's one slide that I always show, and I say knowledge is of two types. One is to know it yourself. The other one is to know where to look it up. So if I go fast today on some of the fundamentals, you can always look this up elsewhere, but to be aware of the principles is pretty important. We take it for granted that some of the jobs that used to take a lot of labor, the industry of horse and cart, there were a bunch of people employed that used to put proper nailing on the calf of the horse so that can run many distances. Some people were in the business of repairing the carts. Some business people were in the business of trading this and so forth. All of that were wiped out by the car industry, right? Because it could do much. We have 200, 300, 400 horses under the hood of a car. Or when you go to dishwashing and laundry and so forth, all of this have been replaced by appliances. So even if you are doing something that is very complicated, but is a routine that gets repeated, we could program it with the computer, and the computer can do it. So if you do have a job that innovation is not in it, then we are really in trouble. I'm not sure what slide I included here, but this is one of my favorite slides. What this one is showing is in year 500, the Chinese, thank you, Dr. Vincey, invented paper. But look in that chart. Pencils was invented in year 1600. That is 1,100 years later, right? And look, it took 200 years further. I'm not sure if Chinese invented eraser, but somebody did. 200 years later, eraser were invented. Today, 90% of Intel's products are from concept to product from January 1st to December 30th of the same year. If the Turkish engineers sitting on the back rows, fresh graduates, think that you're working hard, we have some graduate students in the college when they work with us, when they are PhD students. Edwin was one of those who Dr. Nilüfer sent to us from Technical University, Sempozyum Technical University, or Middle East Technical, one of the two. Okay, Istanbul Technical, all right. So amazingly strong student. came to us, did a wonderful job. He was the one who worked on embedded cooling, brought it to a stage. We worked also hard with him. And then he got employed by Intel. When he was working with us, we were Edwin was ahead of us. He was always bringing work to us, and it took us longer to read it. But ever since he's joined Intel, he would tell you that he works until 6 p.m. or so, then comes home, takes dinner, goes back to his work. Why? Because these companies pay very well, but they also know that they got to invent all the time. By the time you figure out how you do 2 megahertz, they put a 4 megahertz chip on the table. That's how other people cannot reach them. So if you look at profit margins in appliances, you may have heard that GE is trying to get rid of their appliances and give it to Electrolux. Why? Because GE says our typical profit margin in other divisions is 40%, 25%, appliances 5 to 6%. We don't want them. Take them away. Because our refrigerator is looking the same as our parents' refrigerator, is looking the same as grandparents. Things have not changed, right? So innovation is equal to value. Innovation is equal to good standard of living. Innovation is equal to having jobs that other people cannot have. By the way, smartphones' profit margin is 40 to 60%. Because again, they are doing things that others cannot do. When you look around the room, any of these technologies that you see, electricity, nice materials, fertilizers so that people do not die from hunger, bridges, airplanes, communication and all that, all of this is past 100 to 125 to 150 years, right? But if you look at the age of a planet Earth, that's about 4 billion years. If you look at the fossil of a human and so forth, go back. I said, look, how many years? I asked my 9-year-old son, and he says Egyptians, 10,000 years. I said, forget it. Egyptian and all that is only 10,000. We have 4 million years that evidence of some kind of fossils that resemble human. Okay, but nothing like 100 years, right? Nothing like 100 years. So a lot has happened this past 100 years. But you know what? We have reached a stage that things are getting saturated. Except electronics, the airplanes of 1950s were moving faster than the airplanes of 2015. Comparison of horse with car versus car in the past 30 years have not really changed. There has been no paradigm shift. The way we make air conditioners, the way we transfer the energy, the way we do piping, the way we do infrastructure. So to me, there is just tremendous opportunities. Whoever wants to say there is not, I will say there is. And I'll show you, we'll sit down and talk to you. I really find it, I was in administration before I came back to university job, because I find that there is plenty of exciting opportunities that you can tackle that other people are not looking at. This morning I showed you data centers. You could have your own business going and saving people energy and making a contract with them that if I saved you cash, $100,000 per year, and you took 50% of it, I took 50% of it, and I'll pay for our expenses. Sorry, do you mind? And they say no. We have a couple of former students in the US who have opened their own companies doing that. We have charts that will show you out of 100 kilojoules of energy that today comes to US infrastructure, 61% is wasted through waste heat, 39% is utilized, okay? How? Typical cars, typical buildings, typical manufacturing, and so forth. So there is tremendous opportunity from here on to do innovative work in various sectors because, as I said, except electronics, which has introduced paradigm shifts, the rest of the industries have not changed. Appliances, as good as 30, 40 years ago, piping infrastructure, energy infrastructure, how we burn the fuels and so forth, that have not really changed. But to me, from here on, if you are to make big shifts, you have to think about materials. So please, if you have a friend or a colleague in material science, respect them because we really need them. So we have to ask them to develop new materials. After that, we have to be able to make this. We can always compare science and engineering. To me, the biggest difference between science and engineering is engineers apply science, and engineers feel good only when they can do something with science. Whereas scientific people are curious into finding why things happen. Oftentimes as engineer, you're valuable when you leave aside a few percentages here and there, you make an approximation and you make a device. So materials, manufacturing, and innovative designs are going to make big differences. And as I'm showing in here, things have really become difficult. You cannot claim that you can do it all. It's been many years that we have written proposals with just one professor involved. We reached material science people. We have, I'm not sure if they're in these two pictures, we have two people that help us in material science. We have a chemical engineering, Professor Choi. This guy is material science, thermohydraulics, chemical engineer, macrofabrication, nanofluids, computational fluid mechanics, innovative designs, risk and reliability. When we develop a new product, is useless if you cannot demonstrate through accelerated testing that this particular pump can work 10,000 hours, that can work 20 years, based on the models that you have, and so forth. Okay, so what is additive manufacturing? For many years, we did have innovative designs that we were trying to improve air side heat transfer coefficient. Any of you in the business of air conditioning know that when we make a chiller, when we make a condenser, the refrigerant side is a lot stronger heat transfer than is the air side. Agreed? Air is a very weak heat transfer fluid. Therefore, for years, people have been looking at increasing heat transfer coefficient. So what is the heat transfer coefficient on the air side today? If you go to car radiators and so forth, where you have good flow of air, you might get 150 watts per meter square degree K, you might get 200 maybe. If you go to some other applications where the air velocities are stationary slower, you get 50 watts per meter square degree K. What is on the phase change? 10,000 and higher, right? Today in our embedded cooling, right on the back of a chip, we get 400,000 watts per meter square degree K on the phase change through thin film evaporation. So we need to do something about the air side. So we had some very nice concepts. We had patents that we had filed, but we would go to Macrocool in Alabama, and I'm glad to mention their names, and beg them. They had a macro deformation technology that they had bought the patents from Russia, and they could do some very nice features, macro grooves for us. We'll go to them and they said, look, this is time consuming, we cannot do it, and so we'll go to our physics shop, because physics shops do really precision machining, and they would break their tools and they'll say, look, don't come back here because we really cannot do this. So we had this beautiful idea, but we really did not know how to manufacture it until additive manufacturing became affordable. So what is additive manufacturing? You have some concept in mind. It might be complicated, it may not be complicated. It may be something that you may have seen President Obama went to last year to Oak Ridge National Lab, and they had printed a whole car with additive manufacturing. That means multiple components, different components, they all come together. So multi-materials, multi-interfaces and all that you can do with additive manufacturing. So I have a concept that your 10-year-old boy can draw and say, look, this is my concept. We'll make a CAD model of it, right? CAD-CAM. We'll give this CAD model to the computer. The computer will start, and then you leave home. You give this into the computer at 5 p.m., you give it to the machine, and you leave. Tomorrow morning when you come back, depending how complicated this is, from a few hours to a few days, the thing is printed and ready for you to test. That's a capability where now the designer and the manufacturer became the same fellow, right? So layer by layer, you go and put this device together. Whereas if you do chemical etching, you are doing subtractive technologies. If you do macro milling, you are removing the material, right, from a bigger block. So this is why we call it additive manufacturing, in that layer by layer you put together. These are some structures that I think it says courtesy of DARPA, Professor Welcome, who worked at DARPA at a given time. As you can see, you can do structures like this that are very difficult to do with molding, that are very difficult to do with macro machining. Moreover, you can do something like this and you can print electronics on it, right? You can print electronics on it, so this is pretty valuable. If you think additive manufacturing is still academic dreams, no. In fact, you have few companies now that are producing parts for aircrafts, for General Electric, for Boeing, and I've visited some of these entities, they're working 3 shifts. And these companies would argue to you that, in one case, one of the colleagues at Boeing was mentioning, the price reduced by 9 times going to additive manufacturing. You know why? They have parts that are complicated. They have to be brought together, they have to be braced together, and this is an aircraft. Reliability is very, very important. Failures are unforgettable. There are companies who have gone down by just losing one airplane crash, and then the fault being because of some failure, and they lose their business. So they're pretty careful what they do with a particular heat exchanger, what type of brazing and so forth. So additive manufacturing already has applications as such. In this pie chart, I'm showing what industries are using it the most. And basically, you will find out that medical industry, consumer products, and aerospace industry are among the top users. But this is changing very fast. Year to year, this is changing, and double-digit growth, as it mentions here. So are there limitations to additive manufacturing? So we have various methods for additive manufacturing, but predominantly, perhaps I'll go to the techniques, and then I'll come back to this thing here. Predominantly, we have several, maybe 6, 7 different ways of additive manufacturing, but in my group, we work with metal additive manufacturing and polymer additive manufacturing. So we are doing a heat exchanger that out of polymer, and we did a feasibility study for 1 year, then we got a bigger grant for 3 years. What we are aiming for is a plastic heat exchanger that has thermal conductivity of 150 watt per meter degree K. What's the typical polymer conductivity today? About 0.5, about 1, right? So, and how we are doing that? Through composite, through mixing polymers with metals and printing it with a computer. So this is showing you the FDM method, fused deposition modeling. So basically, as the figure shows you, you bring this polymer in here, or polymer composite, and you give it a certain temperature, and you melt the thing in there, and think of additive manufacturing as a macro melting operation. If it's metal, you're doing macro welding. If it's polymer, you are doing macro melting, sorry. All right, so, and then the computer works with this layers by layers and makes this. But again, what is important is in this system, you could now put composites, you could put sensors, and the computer will do it for you. All you have to do, let's say if you were bringing some different materials, you would have another head that would be sitting here, and that head in parallel with this head would be depositing the other material. So going back to as to what we prefer to do today, if you go to one of these companies and you say, look, I want to print this thing, immediately they ask you what material. If you tell them aluminum, they don't like it because aluminum is difficult to produce with additive manufacturing because of oxidation problem. You could have explosions, you could have fires and so forth. So they need special clean rooms where they are careful in terms of how they do it. But stainless steel, no problem. If you have a concept and you want to see it out of stainless steel, really no problem, they will do it for you. Titanium, Inconel, these are high temperature materials. Titanium and Inconel are of interest because we have a lot of waste heat in power plants, in gas turbines, in automotive that we want to recover. And as you know, waste heat becomes interesting when you have temperatures of 300-400 degrees C and higher. Okay, so these materials are perfect for high temperature, but are difficult to machine. But with additive manufacturing, really no problem. So earlier I mentioned what are limitations. well, think of it. It says number one, material properties. If you have, how is this metal printing taking place? Is macro welding, right? So you bring bags of powder, of stainless steel, of copper, of aluminum, you feed them into the machine is bringing this powder to the nozzle and then macro welding, right? So then you put some device together. Would the property of this device be same as bulk copper or aluminum? The answer is, so what I'm saying is, let's look at this thing in here. So let's say this was a polymer and such properties. I gave it to the machine, right? You're saying, no, it's not. Right. Why? Why would it be not? Excellent. It may not be homogeneous. It may be some powders are stuck in the structure in here. And it may be that when you were macro welding, you changed the property of the material because you had temperatures applied at a particular spot and you increase the stresses too much. Okay, among other limitations, you would have the build envelope right now with metals is limited. It's about 1 foot long that you can do stuff. And then tolerances are not as good as if you look at typical baby fin, louver fin. The reason aerospace industry particularly and automotive industry particularly has been successful with these fins because the thickness of these fins is about 300 micron or 250 micron. So really nice small wall thickness. Whereas with some of the metal printing right now, we cannot do that. Cost and speed, we are saying this is evolving. Don't worry because the speed of this machine just past 2 years has increased by 8 times. So what I want to say, the limitations that are listed here are not really showstoppers, meaning that we will find solution for them. Size, people will increase the size of the machine if you found an application, a customer for it. All right, so here is a course that we want to offer in fall 2016. By now, I hope you agree that additive manufacturing is not such a similar to thermodynamics. It's a field that brings material science together, brings CAD and CAM together, and brings design together, right? So look at the topics in this course. You start with some review of traditional manufacturing techniques, then you come up with a couple of weeks of CAD-CAM, and after that you look at different fabrication techniques, and from there we charge the students to go and design creative concepts. So we leave it to the students to come up with a design that they want to build. We're given certain parameters, and they have to prove to us that they found a way to make it. And how they found a way to make it, they have to sit down and write a program. They have to sit down and write a program to make it. Okay, so this is the previous slide for polymers. This is for metals. As you can see in here, unlike your traditional manufacturing, all of this, including the rotating shaft, including the blades, including this arm here, logo here, all of this is done by the computer. Result, you would not have to do brazing later on, patching, joining, and so forth. So this is a major advantage of dealing with additive manufacturing. Okay, so I'm not sure if I helped by convincing you additive manufacturing is good, but let me show you one case study that there is a program that U.S. Department of Energy has, ARPA-E, and is throughout the year is open. Throughout the year is open, and that's called Open FOA, Open Funding Opportunity, and they call it ideas, open ideas. They give you $500K for 1 year to prove your concept. And again, anybody can submit, right? So we did that. We filed one application and we said, look, we have a great idea how to improve the air side heat transfer coefficient. We submitted, they gave us a year. In 1 year, we delivered results that they liked. They gave us a 3-year contract, close to $3 million, to basically go and scale up, right? So I'm going to today show you some of the results that we got in that project. All right, so I'm showing in this slide basically some of the concepts that we are working on. This is moisture zapping from the air. Instead of centrifugal devices, instead of heavy equipment, you could operate, I'm not sure if the movie can play. Nope, probably not. I have to be at the computer to, but the moment you turn the electric field on, the moisture disappears. This is frost formation in the electric field. You defrost the system automatically and so forth. But this is a metallic heat exchanger airside that I want to discuss today. This is a polymer heat exchanger we are developing. And this is some fluid management and evaporators that we have had very good success. So I'll describe this one and this a bit. And this is the one that I mentioned. We can get a thermal conductivity of 150 if it all works out. Okay? So, but again, with additive manufacturing here, this is air-to-water heat exchanger. The entire thing would be printed by the computer. Okay? All right. I still don't think I have convinced you, so let me go to dry cooling of power plants and show you heat transfer coefficient on the air side that with our design are more than 10 times higher than state-of-the-art. What is state-of-the-art? I'm not talking about a dumb plain fin. I'm talking about louver fin. I'm talking about wavy fins that aerospace industry uses. Okay, so today dry cooling is 6 to 8 times more expensive than cooling tower cooling. But why is it that some places are already using dry cooling? In fact, Evapco is one of the companies that make dry cooling. If you ask them, they said they have 6 to 8 to 9 months to 12 months backlog for people who have ordered dry coolers. Wow. Evapco is a cooling tower company, right? Why dry? 6 to 8 times more expensive. Why they are taking orders? Because already in the US, there are several states that have banned use of cooling towers. Why? Because if I look at, let me show a cooling tower picture and see. I'm not sure if in Istanbul you have seen this fog leaving the cooling towers. Some parts of the year you can see it, some part of the year you cannot see it. And you know why? The reason is thermodynamics. Anytime the temperature outside is less than 50 degrees Fahrenheit, that's about 10 degrees C, you could see your breath. You go like this, you could see your breath. So you could see this fog. But 7/24, 365, this water is leaving the towers. Some days you see it, some days you cannot see it. So in 1970s, we used to use rivers and lakes, and we call it one-stroke cooling. So we were not really using a lot of water. We would just mix the warm water with the cold water and would cool the condenser water, bring it back. Then we resorted to the cooling tower issue, but the problem is fast withdrawn of the fresh water from aquifers, and people are not allowing this. And I have charts after charts that would show you why the water problem is a major issue now. So if you look at this chart here, the areas that are red are absolutely serious business, meaning that these people will run out of drinking water because they have been pulling water from aquifers. Just like you pull oil, it's a limited supply. After it's finished, right? If you rely on rains and all that, rains do not help these aquifers unless if you have heavy rains for many years, and otherwise would not take place. So you see, even in the US, you already have red areas and you have orange areas and so forth. So what I mentioned this morning, the cost of energy for water is a major issue that has to be taken into account. So, and we also mentioned the fact that today, the amount of water that we are using for electric power plant, this is not other power plants, just what we call thermoelectric power plants, that is, you burn the fuel, you produce steam, and from there you send it to the gas turbine to produce electricity. They are consuming equal amount of water compared to agricultural use. So that's why the states have put a ban for use of cooling towers, and so we are saying why, first of all, why 6 to 8 times more expensive and people are still buying? Because they have to. But if overnight a company in Turkey developed a dry cooling method that was, instead of 6 to 8 times, was 3, 4 times more expensive, what would happen to that company? It would go out of business and they would order from you, right? And that's where really innovation would make a difference. And you cannot compete with a particular cooling tower company that is in operation now. Why dry cooling is more expensive than wet cooling? Simply because air side heat transfer coefficient is pretty weak. When it goes to dry cooling, we do not benefit from that advantage that evaporation provides. So we have Chilton-Coleman analogy that says when you increase heat transfer coefficients, then you have J factor is a measure of heat transfer, you have pressure drops, but what we understand is that when you increase heat transfer, the pressure drops even go higher. And that's why you stop. You don't develop a fin that kills you with pressure drops, okay? But you can give a CAD drawing to the computer and say, look, I don't want the pressure drops to exceed such and such. I want the pressure drop to stay here. I want the heat transfer to be that. This is my design. You run through optimization. If your computational model told you, yes, that's possible, the computer says, look, I don't know what this is. I'll print it for you. And then you have a heat exchanger that is performing. Okay. So we looked at this was part of what we wrote to get our monies. So we argued that, look, we have looked at all the technologies. In fact, we wrote to some people. There were work from around the world. And we were finding some work sitting here, particularly this work here, electrohydrodynamic enhancement. Somebody had reported, and they were sitting here. We got happy. We said, wow, somebody really violated Chilton-Coleman analogy. Because if you are below this line, any technology that brings you below this line, you have violated Chilton-Coleman analogy, which means you're getting heat transfer, higher heat transfer, and lower pressure drops. We found out this group was not really counting the power that they put into electrohydrodynamic electrodes. Result, they went way back to the left, therefore no attractive. So we argued that, look, one technique that could get you here would be a special design that we'll cover, but otherwise you have seen many work in the past on porous foams, you have seen on lower fins, you have seen this Japanese fin that is pretty attractive and has made very good gains in reducing the pressure drops through some vortices, but at the end, none of them comes below the line, all right? Okay, so the application that we wrote, because even today, there is a lot of programs that will be coming out, and you are welcome to collaborate with investigators in the US. I don't think we will be able to ship money overseas, but we could always have a task that we will do in parallel with you. We can share results, we can be part of a project, and producing results and so forth. But this is a water program that came out and for developing more efficient dry cooling solutions. So this picture is showing you a typical dry cooler. If you happen to be in Las Vegas area, within half an hour from downtown Las Vegas, there is a plant, a hybrid plant that Warren Buffett recently bought. And this plant gives you 65% efficiency, which is pretty good, right? Typical fossil fuel plant gives you about 40–45% or so, but it's working with dry cooling because in Nevada, it's against the law to use cooling towers for cooling. They don't have water. So the heat transfer coefficient, what you see there is a whole bunch of these modules, arrays of them that are cooling this power plant. So the fans are working, huge fans. It mentions some of the dimensions in here. So these pipes are 30 feet long, right? So this could be 30 feet long. This could be 30 feet long. So these fans are huge. They are working for what? For pushing the air through this structure here so that this steam can condense. So steam comes here, runs into these pipes, air is pushed across these fins, and that's how you cool this plant. Does it take a lot of power? Yes, it takes a lot of power to run these fans, right? What's the heat transfer coefficient? I'm showing it in red. It's about 50 to 75 watts per meter square degree K. Okay? Very low. Compared to what you get in phase change, compared to what you get into a faster speed. Okay. So we designed an airside heat transfer design that we said, look, we won't compete with Honeywell Aerospace, we won't compete with Parker Hannifin, we won't compete with this aerospace industry guys who, for the past 50 years, they have developed very sophisticated fins to have maximum heat transfer and to reduce their pressure drops, right? Incidentally, I'm not sure, in this slide I'm not showing. The partners on this project with us were Boeing and Honeywell Aerospace and Baltimore Air Coil. Baltimore Air Coil is a cooling tower company. Boeing and Honeywell are aerospace. Why them? Because they have interest in increasing airside heat transfer. They are not interested in helping power plants. They have interest in airside heat transfer. And today, the project, continuation of the project is being done with Boeing and Honeywell Aerospace. Okay? So they are fully aware of what is out there. And these companies, if you go to them and you say, we'll give you money to come and do a research, they only agree if they think that they can develop a product that they can sell. They are not in the business of doing research. They're in the business of making shareholders happy, right? So that's important. And same thing for universities in Turkey. I think if you go to Arçelik, if you go to other companies and you bring them to be part of your research, if they join, that's good news because they think that you may have results that they can use. Anyways, so what is the difference between this and traditional design? Air is coming through some manifolds, goes into these macro grooves, which are parallel fins. We bring the air, we stay with it, and then we stay with it until it goes out of the heat exchanger. So we're doing a better flow management, okay? The concept may not be that clear from this drawing, but again, think of it that we're doing a better flow management by bringing through these manifolds that you can see the flow in, feeding them to both sides into the heat exchanger, and then again having channels that the air goes out. So good flow management, right? What else we are doing is we are, as shows in here, we bring the air and the air goes 1 millimeter or 2 and then leaves. So we're not letting the air go long distances, and that's why we are really operating in this zone here. We are operating in this developing zone, and we are not coming here. That's why our heat transfer coefficient would be higher. Okay, so then we will go and print this heat exchanger, and then we'll test it experimentally and see what results we get. And that's exactly what we did. So this is our CAD model. This is our CAD model, and we designed it, we run it by our industrial sponsor. They had design review, and then we finalized this design, and now we are going to give this to the computer to print. Think of how you are going to do this thing with macro milling, macro deformation technology. None of that would work, right? All right. So this computer model, so in additive manufacturing, you always design, run optimization, analyze. Only if it makes sense, then you go build it, right? So we saw these green numbers. We said, wow. This is for a 12.2 megawatt heat exchanger for power plant cooling. So we said if this concept works, it's really a solution to power plant cooling because as you can see here, it would reduce weight, it would reduce volume, it would increase the transfer coefficient, it would decrease pressure drops. So this is all fine. Go ahead and try to see if you could make it. So we did. I could have brought samples with us of this heat exchanger. These are small samples, but now we have bigger ones. But in the security checks and so forth, oftentimes they want us to pull this out because inside structure is complicated. They may want to hold it and so forth, so it's not possible to bring it. But again, if you are in the area, we'll be happy to show you. So we printed this heat exchanger, manifolds, and microchannels together. All these manifolds, plastics are also printed with computer. Polymer machine prints this, and they're cheap. The polymers are really inexpensive to print. And the metals are the one that is a little bit more challenging. So we tested in our loop, and then we plot the heat transfer coefficient. We repeat the runs, as you can see, and the runs are pretty repeatable. So what you can see here is on this axis, you can see the Nusselt number, then you go here H, then you go here pressure drops. First of all, look at the pressure drops, how low they are. For the sole reason that we don't let this flow go through a tiny channel long, we bring it, we drop it on the surface, and we take it out. Look at the heat transfer coefficient we showed you. In current system, the value is 50 or 75. And as you can see here, now we are going to heat transfer coefficients of 500. But you know what? This is experimental results, and this is the first printed coupon. So as we print more, we get to know how to do it, we become better at printing. And if I show you the comparison between numerical prediction and experimental, this is what it is, right? So numerical is much better. So the 500, the 600 watts per meter square degree K is experimental value. And we are saying in here, we believe partial blockage of some of the channels and any macro non-uniformity in the channels are mainly responsible for the difference between projected and produced, tested 120 watt coupon heat exchanger. Keep in mind, this is the first ever heat exchanger, metallic heat exchanger that anybody did with the computer. So there's plenty of room to improve, right? So now we go to a second case study, which due to time I will not be able to go and cover the entire study, but you have commercial tubes that Wieland and Wolverine and other people today make for chillers for evaporation, right? So what we said is, can we improve the evaporation process by making jackets like this that can manage the flow on top of these tubes? Okay, so a lot of nice thermodynamics, a lot of nice heat transfer knowledge goes into designing these jackets. Okay, so fundamentals are very important. If you have deep knowledge of heat transfer or deep knowledge of thermos, somebody can use them. So don't worry about the management. Yesterday, one of Professor Nilüfer's students was saying, I'm double majoring in mechanical engineering and management. I told them, look, please focus on mechanical management. You can always learn later on through part-time programs. But solid knowledge of fundamentals and understanding would lead to good designs here. As you can see, the shape of this guy is quite different than this, quite different than that. I think I'm not showing any slides as to what happens, but these structures would, we have movies on this, would make you decide on the size of the bubble on the tube, right? These structures help you manage the flow on top of these tubes, unlike a big bundle that has many tubes that are evaporating. Some of the tubes lower performance in the bottom of the bundle, some of them in the middle, some of them on the top. This one is individual tube, is been fed by refrigerant, and it's too bad that I did not include any visualization for you to see, but the performance is just simply magnificent. We are really hoping this thing will get commercialized. We're working with some partners. And look at here, 90 grams of R134A for a 5 kilowatt duty compared to 1.2 kilogram of refrigerant with traditional pool boiling application. What else? The lightweight 0.5 kilogram or 0.45 kilogram versus 6 kilogram for a similar duty. All of this is because you are impinging the flow on top of the evaporative surface. And as I said, we will control the flow. We'll control the flow as it comes in here, such that, again, if you see the movie, the evaporation process is not comparable to what you see. We call this process intensification. And you ask what is process intensification, we will say is a situation where every molecule of the working fluid is working for you, right? So if you have a 2-inch diameter tube and flow comes in, some flow in the center of the core of the tube is not really working for you, the ones closer to the wall one. But if you pass it through a 500 microchannel tube, the entire flow is working for you because there is no loose room to mendel around and not do work. So with that, I think I'm coming to my messages here. I would pledge to the professors who are the same business as I am that in your classes, please tell students that we need job creators. We do not need job seekers. Some people have to create jobs. And please respect those who are business owners, because it's pretty difficult to own a business these days and stay on top of the waters, right? So the only way that you could stay in business these days and have good standard of living like the way you see it in Istanbul is really innovate. Before people figure out how you're doing it, you introduce a new product. So that's a must, particularly for schools as strong as Istanbul Technical or Middle East Technical. I think we have a duty and to repeat and repeat that, look, you must innovate. I think our homework problems, our exams have to be such that we'll test their innovation. And I hope the industry helps giving opportunities to our young generation to innovate, because without that, we would not be worth before too long. Innovation through integration of computer. AM stands for additive manufacturing. This is a situation where somebody has a concept that concept can be built and tested. Don't shoot him down. Don't say this is too expensive. I could always go back and optimize, and you tell me cost is important, you tell pressure drop important. That's how it happened in this project here. And I'll say, okay, what else is important? You say, these three are very important. I said, am I free for the rest? You say yes. Then I'll run up optimization and I'll come with the design. Then I'll print that design. If you decided, no, the cost is still high, I can go back and reduce the performance. Instead of giving you 10 times better performance, like I'm giving here, I can give you 2 to 3 times better performance, but then reduce the cost and do something with it. Then you can bring engineers in to give you other ideas, but it is really valuable that somebody is building a concept that you can test it like we did here. We are talking about Internet of Things, right? Even Ashtray is looking into, before too long, we would like to see what our pump is doing. We would like to see what our heat exchanger is doing. And heat exchanger, even greater goodness, touch you are important. Human body, thermal management is pretty important. So if we could embed sensors in heat exchangers to warn us of any stress, to warn us of any excessive performance and so forth, that's very valuable. Additive manufacturing makes you do that without any complexity. Message number 4, AM is evolving very fast. So printing speed in the past 2 years have increased by 8 times. Cost is really substantially coming down. So do not let this thing shut you down in terms of opportunities that provides. So I'll go back to what I said earlier. We need in this business of HVAC, we really need innovations, big time, that we could come up with products that people would not be using other products. Car industry got out of the slump by introducing electronics in the car. Today you buy another car not because your car doesn't work anymore, because of the sound system, because of electronics that warn you if somebody gets too close to you, because of the back camera, because of the internet access inside of your car, and all of this is affordable cost. How affordable? Because volumes are very high. They have got mass produced. Pressure in the tires, a few years ago used to be very expensive, but now they're cheap, even lower priced cars have it. And with that, I would say this is a picture of a book that says the world is flat. Basically says the intellectual capital, the money, and the people go wherever they find a better bed to rest. So it might be Istanbul, inshallah, as you said, but that requires your innovation. And with that, I think I'll come to an end. Thank you very much.
Do we have a few minutes for question and answer?
Maybe 2 minutes because we have to leave this room.
Okay, 2 minutes, maybe just 1-2 quick questions.
Okay, sure.
Maybe later during
All right.
the social hour.
Thank you, thank you.
Okay. Thank you very much for everyone. Thank you, Mike, for your very nice speech. Thank you.
Our chairman and our speaker. So we will have a short book presentation by Professor Dr. Birol Kılkış, a short presentation. Hocam buyurun.
Evet, son dakika, son birkaç dakikanızı alacağım. İlgilenirsiniz diye bu birleşik ısı ve güç üretimi konusundaki Türk Tesisat Mühendisliği Derneği'nin yapmış olduğu yeni bir yayın var. Çok kısaca hani belki içine bakmaya fırsat bulamazsınız. İçeriğine göz atmanızı sağlayacağım. Bu Türk Tesisat Mühendisliği tarafından basılan kitap aynı zamanda İngilizce çevirdikten sonra ve biraz da içindeki bilgilerde bazı Türkiye ile ilgili bilgiler ve onlar da Amerikanlaştırıldıktan sonra aşire tarafından basılacak. Evet. Hep söylüyoruz bu toplantının adeta motosu oldu. İşte ekserjiyi kullanıyoruz, enerjiye para ödüyoruz ile başlıyor kitap. Ve bu başlangıçlarda anlıyorsunuz ki kitap ilk defa olarak ekserji tabanında bir birlikte ısı ve güç sistemini inceliyor, çözümlüyor ve sonuçlara tüme varıyor. Bu bağlamda görüşü ve vizyonu açıcı, yenilikçi, yeni ürünler tasarlamanızı sağlayıcı bilgiler, vizyon açıcı, ufuk tarayıcı bilgileri sizin ekserji tabanında düşünmenizi sağlayacak yeni bir kitap. Yani içinde kojen nedir, kojen nasıl yapılır, kojen motorun tipi nedir, neyle çalışır, nasıl çalışır, nasıl bakım yapılır gibi standart bilgiler yok. Burada kutucuklar var. Kojen şudur ama girdisi bu, çıktısı bu, özelliği bu, ekserji verimi bu. O şekilde birisi ısıl sistem tasarım mekanizması sunuyor. İşte burada görüldüğü gibi bir kojenerasyon sistemini ekserji akış çubuğu denilen yeni bir yöntemle analiz edebiliyorsunuz. Verimleri buradan görebiliyorsunuz. Nerede ekserji yıkım var, nerede verimlilik var onlara bakabiliyorsunuz. Bütün bunları anlatıyor ve esas tema her uygulamada olduğu gibi arz enerjisinin veya ekserjisinin taleple dengeli olması lazım. Dengesiz olursa dengesizlikle orantılı olarak orada bir ekserji yıkımı var. O da biliyorsunuz geri dönüşü olmayan bir yıkım. Irreversible. Bu bağlamda bir de madem ki konumuz, kitabımız bir yenilenebilir enerji kaynakları konusunda birlikte ısı ve güç diyoruz. Demin bahsettiğim gibi panelde artık 4. nesil bölge ısıtma sistemlerinde rüzgar, güneş, jeotermal ne varsa atık ısı hepsi bir arada kullanılmak durumunda. Türkiye'de böyle bir kompozit harita yok. Rüzgar haritası var, güneş haritası var ama bunları üst üste koyduğunuzda ne olabilir? Ekserji tabanında özellikle nerelere gidebilirsiniz? Nelerden faydalanabilirsiniz? Bunun açıklayan böyle bir harita nasıl yapılabilir? Neden yapılması lazım? Bunları da açıklıyoruz. Denklemlerle. İşte düşük ekserji binası diye bahsettim panelde. İşte bu mesela İsveç'ten bir örnek. Toprak ısısını doğrudan doğruya kullanan bir sistem. Tamam kullanacağız da bunu nasıl kullanacağız? İşte mesela döşemeden ısıtma. Aşağıdaki bazı abaklar, handbook'tan benim hazırladığım bazı bilgileri buraya aktardık. Copyright nasıl olsa bende diye. İşte akılcı ekserji yönetim modeli, Rational Exergy Management modeli çok detaylı anlatıyoruz. Bir de kitabı inceleme fırsatınız olursa veya almak, şununla karşılaşabilirsiniz veya beni kritik edebilirsiniz. Ya çok tekrar var. Orada da anlatıyor, burada da anlatıyor. Niçin tekrar var? Şunu düşündük. Bu bir el kitabı şeklinde olduğu için her chapter, her fasikül kendi içinde tutarlı olmak durumunda. Dolayısıyla konu da gerekiyorsa diğer chapter'lara bakmanıza gerek kalmadan bazı bilgiler orada da tekrarlanıyor. Tek başına o konu mesela siz sadece akılcı ekserji yönetim modelinde ilgilenebiliyorsunuz. Diğer kısımları okumazsınız. Orayı okursa ama o konuyu iyice açıklamak gerekiyorsa başka chapter'lardan bazı bilgiler ithal edilmiş vaziyette. Öyle bir denge kurduk. Bu arada bunu da şöyle söyleyeyim. Kitabı sadece ben yazmadım. Kızım şiir kılkış TÜBİTAK'ta uzman. Onu da birlikte yazdık. Bu REM modelinde geliştiren kendisi. İşte bunlar tipik slide içindeki görüntüler. Kojenin anlamı nedir? İşte bir PVTC sistemi, yani madem konumuz yenilenebilir enerji kaynaklarıyla ısıtma, soğutma yapmak, işte bu nasıl yapılabilir? Burada görüldüğü gibi işte örneğin Bir PV'nin arkasından su dolaştırıyorsunuz. Isıyı ve elektriği çekiyorsunuz. Binanın içinde ise termoelektrik elemanlar var. Elektriğin bir kısmını talebe bağlı olarak ya ısıtmada, radyant panel olarak TEG'lerde veya soğutmada kullanıyorsunuz. Orada çektiğiniz ısıyı soğutmada ve TEG'in ürettiği ısıyı tekrar çekip hatta istemediğiniz kadar da ısı elde edebiliyorsunuz. Bu gene Hollanda'dan, işte kitapta bir sürü örnek var. Bu da rüzgar arpı. Hollanda Delft Üniversitesi'nden bir rüzgar türbiniyle güneş panellerinin tümleşmesi. Bu bir restoran, bir turistik şey. Burada işte gergi tellerine asılı foto gözeler demişiz. Bunlar aslında şuralara asılı fotovoltaikler. Gergi tellerin gergisini değiştirerek sicim gibi güneşi takip ediyor. Ve dolayısıyla güneşi takip eden bir PV sistemi artı rüzgar türbini yan yana. Bunun gibi örnekler kitapta bolca var. İşte bu da çok basit bir kendi evinizde yapabileceğiniz melez sistem. Rüzgar türbini de var, PV var. Burada dikkat edecek şey bakın, rüzgar yok o anda. Rüzgar hiç çalışmıyor, elektrik üretmiyorsa ama PV'ler çalışıyor çünkü güneş var. Onun için zaten melezleştirmenin temel sebebi de rüzgar ve güneşin hemen hemen arada 6 saat fark olması. Güneş ışını en yüksekken rüzgar olmayabilir öğlen vakti. Ama akşama doğru veya sabahları daha güneş ışınımı yeterli düzeye gelmediği zamanlarda rüzgar olabilir. Bu ikisi birbirini tamamladığı zaman 24 saat boyunca sabite yakın, yani tam sabite ama sabite daha yakın çözümler elde etmek mümkün. Onun için de melezleşme sistemi bahsettik. Solar Decathlon'dan bahsediyoruz. Örnekler, birkaç bina örneği var. Bu ODTÜ'nün yaptığı ama yeterli sponsor bulamayıp gidemediği güzel bir proje. Bunun da mentoru bendim ama gidemediler. Bu da şunu gösteriyor. Hakikaten bu tip projelere sanayicisiyle, mühendisiyle, derneğimizle sahip çıkmamız lazım. Kim Türkiye'den en iyi proje yapıyorsa onu desteklemek hakkı. Destek istemesi hakkı. O konuda da çalışmalar derneğimizde devam ediyor. Sayın Profesör Nilüfer Eğrican bu konuda değerli çalışmaları var. Sorusu olan kendisinden bilgi alabilir. İşte melezleşmenin değişik yöntemleri var. Bunlar artık biraz detay. İşte PV ile PVT'leri mukayese ediyoruz. Seçime faydalı bilgiler veriyoruz. İşte low exergy building dediğim zaman radyant tavandan ısı borularıyla ısıtma ve soğutma yapılmanın yeni bir teknolojisi. Yarın bu konuda bir makale var, sunu var öğrencim tarafından. Abaklarımız var. Hani her şeyi bilgisayara yüklemek yerine abaktan hala eski alışkanlıklar, hatta slide rule tipi şeyler kullanılabilir. Bunlarla ilgili çok basit kullanılabilecek, hatta size nostalji yaratabilecek eski yöntemlerimizden de bir kesit sunduk. Orada değişik yöntemler var. İşte ekonomik olmazsa olmaz, ekonomiyle ilgili bir chapter'ımız var. Bölüm 12. Enerji depolaması çok önemli. İşte alternatif enerji sistemlerinin melezleştirmesi, yeni ufuklar. Bir de bölüm 16. Bu ise lejyoner hastalığı. Çünkü low exergy dediğiniz zaman düşük sıcaklıklarla çalışıyorsunuz. Açık devreli sistemlerse kullandığınız lejyoner hastalığı önemli oluyor. Mesela kullanım sıcak suyu. Bir düzlemsel toplaştan 40 derecelik su size yeterli gelebilir. Onunla elinizi yıkayabilirsiniz belki, duş alabilirsiniz ama aslında çok büyük risk. Çünkü lejyoner hastalığın ürediği en tehlikeli sıcaklıklardan birisi 40-45 derece. Bunu önlemek için en az sizin servis suyunuzun 60-65 derece musluğa gelmesi lazım. Orada siz onu haşlayacaksınız. Bunu yapmazsanız ki bu işte bir bakanlık, Sağlık Bakanı yönergesi aşağıya bu konuda yeni bir standart yayınladı. Buna da önemsememiz lazım. Yani düşük sıcaklık derken de dikkat etmemiz gereken önemli kısıtlar var. Bunu hatırlatmaya çalıştık. Sonuç olarak işte değişik bina örneklerimiz var. Bir eser binasından, Amerika'dan kendi çalıştığım konular. Otomasyon önemli. Onları da bir noktada kitabımızda yayınlıyoruz. İşte diğer appendixler var. TTMD 48, cilt 48'in eki aynen yer alıyor. Aşağıdaki conversion chart, tahvil tabloları vesaire. Yani bir tasarım için gerekli bilgileri ufuk genişletici, ufuk tarayıcı bir bazda sunmaya çalıştık. İlginize teşekkür ederim.
Dear participants, this is the end of our sessions for today. Now you can use our session rooms besides for your free time and for your networking meetings. Thank you very much for your participation.